This video goes over how to calculate the rate of change. And so the rate of change is a comparison of two values with two different units. We've done this before, finding the slope. We've seen it before as the expanded version of that formula, y2 minus y1 over x2 minus x1, where x1, y1 and x2, y2 are two different points on the graph. In function notation, we can label those 2 points as x1, f at x1, which is really just y1. And here we've got x2, and then f of x2, which is really just y2. And then we can use our same slope formula or the difference quotient formula, which is a fancy way of saying the slope. So we can calculate the average rate of change of the temperature based on a graph here. And so our first one that we're doing is we're changing from 4 a.m. to noon. So this is x1 and x2, and our corresponding y values are the y values of those points. So here at 4 a.m., this is our x1, f at x1, and then our noon, which is right here, is x2, f at x2, and then we can put those values in to our slope formula. So our difference quotients formula is f at x2 minus f at x1 over x2 minus x1. You can write it the other way around as written here, as long as you go the same direction. It does not matter. And then we can substitute in our values here. So our f at x2 value is 14, just from the graph. 14 take away 5 over 12 minus 4, which is going to simplify to a value of 9 over 8. We can continue on to a decimal value, 1.125 degrees Celsius per hour. A rate of change always has units if it's referring to a real life thing. So now we go to our second time slot, so 3 p.m. to 8 p.m. So 3 p.m. is right here at 1500 hours. So this is our x1, f at x1. To 8 p.m. So 8 p.m. is 20 right here. So using 24-hour time. So then we've got x2, f at x2 for our second one here. And then we're going to substitute into our formula. So our x2 value, I'll write these 2 points on the side this time. So our first one is 15. And actually 15 happens to be our x value, 15 and 19. And then our second one is at 20 and 11.5. So those are our values that we're substituting in. We're finding the difference between our y values. So 19 take away 11.5 over 15 take away 20. Which then gets us to minus 7.5 over 5, or 7.5 over minus 5, which we can simplify to a decimal value of minus 1.5 degrees Celsius per hour is the rate of change between those 2 points. We're going to do one more from noon to 6 p.m. So we've got our noon is right here, actually the same point that we used before in the first one. So this is our x1, f at x1. And then our 6 p.m. one would be 1800 hours, which is right here. If you notice, those are actually on the same y value there. So we've got f at x2. So when we go to look at those values, our first point is 12 and 14, and our second point is 18 and 14. So now when I find the difference between my y coordinates and the difference between my x coordinates, this says that there is a rate of change of 0 degrees Celsius per hour between those two values. So we can also find the rate of change using a formula. And so when we are given a formula or a function, we can actually figure out a way to calculate the average speed from any time A to a time X. And so that means A is our X1 and our X time is our X2. So when we go to find the slope, we're going to find our f at X2 minus f at X1, or you can go the other way around, it doesn't matter for here. And then we're going to go X2 minus X1. So when we go to substitute in our values, f at X2, which is X, is our function evaluated at X. And then we're going to take away our function value evaluated at A. So 5 times A squared all over X minus A. We can actually use this now to find the average speed from 3 seconds. So this is our X1, or our A value, to 3.1 seconds, which is our X2, or our X value. So when we go to find the slope, I'm going to do 5 times 3.1 squared minus 5 times 3 squared all over 3.1 minus 3, which when I use my calculator to do this, I get 30.5 meters per second is the average speed between those two times. So let's try another example from A to X, where A is X1, X is X2, and now we've got a fraction, and we're looking for a formula for our average rate of change. So we are going to do our function, so X cubed over 55 minus A cubed over 55 all over X minus A. That is our formula in general. And then we can use our formula to substitute in to find our changes from 8 to 8.01, which is from A to X. So now we can substitute in, so X cubed would be 8.01 cubed over 55 minus 8 cubed over 55 all over 8.01 minus 8. When I can use my calculator to simplify this to get a decimal. I would get 3.5 meters cubed per second, which tells me how quickly the volume is changing per second between those time intervals. Our last one is going to combine a table and a graph. So the first thing that we're going to do is determine our average rate of change between 0 to 10 desks. So I'm going to circle here. This tells me that my cost at 10 desks is $15.9 thousand, and my cost at 0 desks is $5,000. So when I go to set up my average rate of change, I'm going to take the difference, my f at x value, which is the function at 10, take away my function at 0, all over the difference between those two x values. So here at 10, this part here represents the part in the table that I've circled out in green. And then the second part here represents the part in the table that I've circled out in blue. So then I can put those numbers right away. I don't actually even need to use my equation. I've got 15.9 take away 5 divided by 10, which is $1.09 thousand per desk. As the rate of change. And I can actually repeat the same thing between 10 and 30 desks. So then I would start my setup like this. 10, and then I have 30, take away 10. I'll use red this time. Circle the red coordinates in my table. And I'm going to use green again for 10 because that matches what I've already circled in my table. So now I can put those values for my rate of change. I'm comparing the difference in the y values over the difference in the x values. And when I simplify that, I get a shallower rate of change. It says that it's $0.37 thousand per desk, which makes sense because that section of the graph is a little bit shallower in between, if I highlight here, in between 10 and 30. If I were to draw a line in there, that is a little bit shallower than the line in between 0 and 10. In terms of manufacturing, often makes sense. As you create more of a singular item, the production cost tends to decrease per item. So let's do one more example here. This is just the average rate of change for a more complicated function, but we're still going to use the same method. This is my first x value. This is my second x value. So in order to find the average rate of change, I'm just looking for the slope between those 2 points. So I'm going to start with f at x2 minus f at x1 over x2 minus x1. You could also do x1 minus x2. It doesn't matter in this case. Here, my f at x2, I've got 8 squared minus 8 all over 8 minus 2. That is just taking 8 and putting it into the function. And I'm going to do the same thing on this side except with 5. So I've got 5 squared minus 5 over 5 minus 2 all over 8 minus 5. When I simplify this, I'm going to get 56 over 6 for the first fraction, 20 over 3 for the second one, 3 on the bottom. Simplifying that gives me an average rate of change of 0.9. We change this to a common denominator. We're going to have 56 over 6 minus 40 over 6 all over 3. 56 minus 40 is 16. 16 over 6 and then divided by 3, which is 16 over 6 times 1 over 3, which I could divide these two. 16 divided by 2 would be 8 and 3, which would simplify to 8 over 9, which would work out to 0.9.